Right now we are in the third generation still. So now the what is regeneration of functional tissues is it should be bio-interactive. That means it should interact with the surroundings of the body where it is placed, and it should be resorbable, of course, and it should stimulate specific cell response. Okay, it should also stimulate the response, cell response, and it should aid the health, aid the growth of the cell and proliferation of the cell. So these things are what we want in the biomaterials. So that's how these biomaterials have evolved from 1940 to from 2000 onwards. We are in this era of third generation. Now, how biomaterials interact with this living organism is, so in the first few nanoseconds of the interaction, the water content in the body will try to react with the biomaterial, and for a few seconds, depending on whether it is hydrophobic in nature or hydrophilic in nature, the water gets absorbed on the surface, and then later in a few seconds, then protein starts to absorbed on the surface, and forms as a layer of protein, and then in few hours this cell attachment also starts starts getting attached to the biomaterial, and then slowly it will the differentiation and migration also will happen. That means this is called cell proliferation. Okay, that also happens. So this is what is generally the interaction between a biomaterial and living organisms. That's what will happen. Now, the causes of the implant failure. Why an implant fails? In what all situations it will fail is, one is by wear and tear, wear and corrosion, okay, of an implant. For example, if you see knee implants or hip replacements, the wear and tear will be more because the implant is the ball and socket joint of a hip implant. So between these ball and socket, it constantly, because of the rubbing action, the wear can happen. So, and these wear debris uh, can cause some problems, inflammation, and all these things. Then finally, it will damage the cells, and it may finally lead to the revision surgery. And some other failure of causes of failure implants is the fibrous encapsulations. Okay, this results in non-bonding with the surrounding tissues. So once this fibrous encapsulation over the biomaterial happens, then it will not have any bonding with the surrounding tissue. That could be a problem. And inflammation, that is rejection. Okay, if it is recognized in the body as a foreign body, then body may reject it. So then inflammation happens. This is also failure of implant. And sometimes in some cases, low fracture toughness, low fatigue strength, especially in case of orthopedic implants. If you see, low fracture toughness and low fatigue strength may lead to the failure of the implant and lead to the revision surgery. And mismatch in modulus of elasticity between bone and implant. This is the case occurs in the orthopedic implants applications especially. So what happens if the modulus of the bone and modulus of the orthopedic implant varies or changes? If there is a mismatch in the modulus, then there's a phenomena called stress shielding. The stress shielding in the sense, so when a load is applied on the body, the among this bone and the implant, whichever is having high modulus, that will take the whole load. So obviously, when you consider steel and titanium and all these implants, the modulus of elasticity of steel and titanium are much higher compared to the bone. So once the load is applied, so most of the load will be transferred to the high modulus stainless steel implants or titanium implants. Then what happens is the bone becomes completely inactive. And when a bone is inactive, it can resorb. It will completely resorb, and bone density will decrease. So it will completely becomes useless. So to avoid that, we need to have an implant which is the whose modulus is close to the bone. So that will be the best idea. So even this kind of stress shielding effect also causes the implant failure, and then finally we may have to remove the implant and replace it. So all these failures requires finally revision of surgery. So which is extra burden for a patient. So this is where we need, okay, these are all the factors which I have explained. This is where we need biodegradable orthopedic implants in the body, because there are very various problems with the existing orthopedic implants like stainless steel and titanium. One problem is that the main problem is that non-degradability of these implants. And because once the surgery is over, um, uh, it takes 2 3 months maximum to heal the bone. And during this, after these 3 months, there is no use of these temporary implant materials, and it can be removed actually. But most of the patients, just to avoid the revision of surgery or secondary surgery, they'll just keep it in the body. Because of that, what happens is in the long term, anytime any infection can happen, especially when a patient uh, is having multiple other problems, like maybe he's diabetic or some other problems. So if he's having any other health issues, so that may it may affect this site of implantation also. Then inflammation can happen at that time. So uh, on the whole, it is not advisable to keep these implants for longer time in the body. So what if we have a implant material, orthopedic implant material, which can degrade in the body? So that is one reason why we have to think about degradable orthopedic implants. And second thing is, when the patient is having an implant inside his body, he will not be able to go for MRI scans and everything, because these magnetic rays can interfere with the implant material if it is a stainless steel. So these for these things, he will not be, I mean, allowed to do that. So that is a big problem again. So all these things, and other thing is what I have just in my previous slide I have explained you. That is another thing is the mismatch of modulus of elasticity, okay, between the bone and this thing. So bone and the implant material. So when you can see stainless steel and all, they'll have a very high modulus of elasticity. So now when we consider all these factors, then magnesium is the only one metallic implant or metallic material which can be used as orthopedic implant material. Why? Because magnesium is highly degradable. So it's actually magnesium. Everyone knows that magnesium is highly corrosive. It's actually a bad property, but we can use it for our advantage in this case. So magnesium having a very high corrosion rates, so we can use that as a um, degradable implant material in as a orthopedic implant material. So if we start discussing about magnesium, magnesium has very good advantages, and especially its lightweight, low density material, and high strength to weight ratio. So all these, and of course degradable. So owing to this, the advantages of this magnesium, it can be used in many industries like aerospace, automotive, electronics, and also another field is biomaterial field. So in case of biomaterials field, because we will discuss more about biomaterials. So in the biomaterials field, how advantageous magnesium is, because the magnesium is very biocompatible. It's already proven. Even our body is also having magnesium in some amount, and non-toxicity. It's not toxic to the body, and biodegradation. That's what I told you just now. It can be degraded in the body, and good mechanical properties or enough mechanical properties. And to throw more light, I have given over here the comparison chart between various other materials and magnesium in comparison with natural bone. So mainly, if you see here, the elastic modulus of the natural bone is around 3 to 20, and magnesium's is 41 to 45, and titanium is around 110 to 117, and cobalt chromium 230. Stainless steel is 189 to 205. So highly, these are all in a high range, titanium, cobalt, chromium, or stainless steels compared to the magnesium. And magnesium's elastic modulus is close to that of the natural bone. So the so we can expect that the stress shielding effect will be very less. And all the other properties, of course, density is very low. That is also one very good advantage compared to all other materials. So the patient will not feel that that implant is heavy or something. So that's a very good, good property. So all these, owing to all these good mechanical properties, so magnesium could be as used as a biomaterial or orthopedic implant material. So now, how this magnesium has evolved and what is its history? It dates back to 1870s. So in 1870 itself, they have used the magnesium in the biomedicine, and then later on they have started using magnesium wires to prevent bleeding, like stitch for stitching and everything. So as a biodegradable implant itself. Then 1892 to 1898, they started using pure magnesium to produce fixator pins and wires, plates, and nails. And then again in 1906, they have started using implants to treat fractures and surgeries. And 1938, using magnesium manganese alloys to as a thin screws, and in the again the orthopedic applications. But somehow later on, slowly they have. I mean, the research is going on, but they haven't. It didn't picked up much about magnesium being used as orthopedic implant materials. And later on, again, it picked up in 2003. They started using again. They invented this magnesium stents for cardiovascular applications. And in 2013, we can see the magnesium zinc alloy being used in urology. And in 2014, uh, magnesium yttrium alloys came up, and uh, they have they have used it for various applications like stents and other applications, and also tried for the orthopedic applications and so on. And from there on, and it is continuing still about magnesium being used as orthopedic implant material, as a biodegradable orthopedic implant material. And now, even though we have discussed that it has magnesium has a lot of advantages like biodegradability and uh, low density, and then high strength to weight ratio, and uh, say that low modulus of elasticity is close to the bone. Even though all these properties are favorable, we do have challenges using magnesium as a biomaterial. So that is the primary one is high corrosion rates. Even though it can degrade it is degradable, and we can use it as a degradable material. If it is the corrosion rate is so high. Sorry. So the corrosion rates of the magnesium is so high that it can degrade even before the bone heals. Okay, if that happens, then the loosening of the implant happens, and then it will be very difficult. So that is one big problem with high corrosion rates of the magnesium, and we have to actually take care of that high corrosion rates of magnesium. And because of high corrosion rates, the hydrogen evolution also happens. So this hydrogen, the more faster corrosion happens to the magnesium, and more hydrogen keeps evolving. So we need, and these hydrogen forms as pockets, okay, gas pockets under the skin, and that will cause a problem. So this hydrogen evolution should also be taken care. And then magnesium is not a bioactive substance by itself. So unlike titanium, if you take, it's a bioactive. Uh, it is by itself is a real. It's bioactive. So it's not like titanium. Magnesium is not like a titanium. It's not bioactive by itself. So, and another big problem with the magnesium is room temperature formability. We have already discussed that even the manufacturability of the implant should also be good. So even in for that matter, if you see, magnesium is not the formability. I mean to say, formability is not that good. Okay, so that is because of the structure, HCP structure. Very less number of slip systems are present. So because of that, it has very poor formability in the room temperature. So these challenges need to be addressed. So how can we overcome these limitations of magnesium? This magnesium, so basically here you can see the corrosion and degradation is one problem, and room temperature formability, and ductility are the problems. So how can we improve this corrosion and degradation is one way of improving the corrosion resistance is by alloying magnesium or making a composites. And another way is by surface modification. If you modify the surface, like for example, give a coating, then you can improve the corrosion resistance of the magnesium alloy. And room temperature, ductility, or the formability, if you want to increase, again, alloying and composites plays a role in improving its room temperature formability. And of course, severe plastic deformation. If you make the magnesium undergo severe plastic deformation, then there are you can improve the formability of magnesium also. Now, say now we have, what are the magnesium alloy systems are there? Generally, the most alloying elements, most widely used alloying elements for the magnesium is like calcium, zinc, and lithium, and strontium, tin. So there are over these many years, okay, researchers have uh, tried or researched many alloy systems. So out of that, some of them I have listed out here. So binary alloys, if you see, most widely researched binary alloys are these magnesium calcium, magnesium zinc, magnesium strontium, magnesium silver, and magnesium lithium, magnesium, and with rare earth elements. And likewise, we have ternary alloys and quaternary alloys, okay, in combination of these materials. So all these alloys have been widely researched, and why we have chosen these kind of elements is because each and every alloying element has a particular uh, property which by alloying which it improves. So, for example, if you take aluminum, it increases hardness, strength, and castability. And zinc improves fluidity of the gas and reduce the hydrogen gas development. And calcium, it improves thermal mechanical properties, creep resistance, and grain refinement, and so on. And if you see silver improves silver is antibacterial, so it can improve the antibacterial property, and also it improves the mechanical properties and age hardening properties. And cerium can improve corrosion resistance, and so on. So many alloys I have listed down here. Most widely used, these are all the most widely used alloying elements in magnesium. So, and a tin, okay, the you see the manganese increases corrosion resistance, and copper also increases both room temperature and high temperature strength. And tin, for example, if you take, it will improve the ductility and reduces crack during processing. So on the whole, you can see that these each and every alloying elements is showing some kind of property in magnesium. So alloying is one way we can actually address the problem of corrosion resistance and improve the bioactivity also. So all we need here to use magnesium as a biomaterial is one is to reduce the corrosion resistance and to improve the bioactivity. So these are the main aims you have to keep in mind when you want to use magnesium as a biomaterial and as orthopedic brand material. So we have done a lot of research and in the field of magnesium, and one of which is we have worked on magnesium tin alloys. So I'll present what we have done and what are my observations on these things. So let us take magnesium tin alloys for orthopedic implant applications, and uh, uh, we have assessed their properties by increasing the amount of tin, like 1 weight percentage and 5 weight percentage and 10 weight percentage. So with the increase in tin percentage, what exactly is happening? What physical properties are changing and how the bioactivity is changing, how the corrosion is changing. All these things we have checked. So if you look at the X-ray diffraction of these magnesium 1 tin and 5 tin and 10 tin, you can, I have marked it here. I think it's very clear here. So you can see basically magnesium tin alloys. When we talk about magnesium tin alloys, so with the little percentage of tin, even below one percentage of tin itself, we will start to see the intermetallic compound Mg2Sn. So if you look at uh, the phase diagram of magnesium and tin system, you can clearly see that magnesium tin Mg2Sn phase will form, intermetallic will form. So the same Mg2Sn we can find here as a peak. So it's very clear that you can clearly see in this peak, particular peak, Mg2Sn peak in case of magnesium with 5SN and magnesium with 10 tin. Okay, so we can clearly see the Mg2Sn peak here. Of course, we are not able to see in magnesium 1 tin. Probably the content of Mg2Sn is very low. So because of that, it is maybe below the detection level of XRD. So maybe we are not finding the peak of Mg2Sn. This is the scanning electron microscope picture of these three alloy systems. So we can clearly see uh, this is a magnesium 1 tin, and this is magnesium 5 tin, and this is magnesium 10 tin. So you can clearly see that the grain size is reducing. So it's the increasing with the increase in percentage of tin, the grain refinement is happening, and of course with the same uh, the the content of Mg2Sn is also increasing, of course. So we can clearly see here in this micrographs that there exist totally three phases. One is this alpha matrix phase, alpha magnesium phase. that is here. And then in the grain boundaries, we can see a light gray color and the bright phase, some kind of bright phase. So if we look at these ADS elemental mapping, we can clearly understand that the bright one is a tin segregation. And exactly where the bright phase is there, we can see clearly the tin content being very high. And in that, like for example, this is the light gray phase. Okay, that where it's not. This is not tin is not much present here, and the magnesium is present here. So probably this we can consider this as a Mg2Sn phase. So we have Mg2Sn and some part of tin segregation also in the Li. So that's what it is the physical features of the various Li systems in magnesium with tin. And if you look at the corrosion aspects of this magnesium tin system, so of course, at the end of 72 hours of immersion test, the magnesium 5 tin shows a very good corrosion resistance, high corrosion resistance compared to other magnesium 1 tin and magnesium 5 tin. So even though initially they in a short time immersion they exhibit almost similar corrosion properties, but over the period of time, if you see, by the end of 72 hours, the corrosion resistance of the magnesium 5 tin is much better compared to the other alloys. And this is the bioactivity of these three alloys. Okay, magnesium 1 tin alloy and magnesium 5 tin and magnesium 10 tin. If you see here, it's very clear. So the what we are seeing here, what we are trying to look at here is the calcium phosphate formation, or we call it as a biomineralization, whether or apatite formation. So whether this apatite has formed or not, how good it is formed. That's what on that basis we can say whether it is bioactive or not. So if you see here in magnesium 1 tin and 5 tin, we can see clearly the this apatite formation is very nice. And in magnesium 10 tin, the morphology completely changes. So I don't see that any like pearl-like structure here in this. It has some other kind of structure, like network kind of structure. And if you look at the elemental mapping, it's very clear that in these two, 1 tin and 5 tin, we can clearly see the calcium and phosphate presence. Okay, and this very clearly full of calcium and phosphate. So indicating that this is some kind of hydroxyapatite formation or biomineralization has occurred. Then whereas in this, okay, this is the magnesium 10 tin. Okay, so you can very clearly see that calcium phosphate content is very less, and oxygen content is more and magnesium content is more. That means it should be a magnesium hydroxide layer and not the apatite layer. So on the whole, we can understand that magnesium 1 tin and magnesium 5 tin has a very good apatite formation as compared to magnesium 10 tin. So probably the more the tin content, probably I can attribute that to the uh, because of the high content of these intermetallics and all. Probably the corrosion rates are very high, and we can also we have already seen here also the corrosion resistance also has come down. So probably that's the reason why it's not showing a highly bioactive. And out of among all these three, magnesium 5 tin seems to be a little good and even in the bioactivity aspects. So on the whole, we have concluded that the 5 tin is the 5 is the optimum percentage of tin which can which can be a potential candidate for biomaterial applications. And beyond 5%, probably the properties deteriorate. So that's what was the conclusion from that studies. And then we have also prepared composites of magnesium tin alloys. So we have taken magnesium tin alloys, same thing, and then we added hydroxyapatite into this alloy to see whether the bioactivity is increasing more, because hydroxyapatite is already known bioactive substance. So the idea is to make the composite with the magnesium tin. Already we have proved that magnesium tin alloy is good, so it can be used for biomaterial applications. And then so let us see. We wanted to see whether we can add hydroxyapatite and improve the bioactivity. And so we have done. And yeah, so because of the addition of the hydroxyapatite, we have already also, apart from magnesium Mg to Sn phase, we have also found some other phases, that is calcium tin CaSN3. That means some part of hydroxyapatite has dissociated and reacted with tin, and it has formed the calcium tin intermetallic, so which can be seen here. There's an extra peak compared to pure magnesium and pure magnesium and HA. So these are the phase contents of magnesium tin with HA and magnesium with HA and the pure magnesium. Okay, so and if you look at the same scanning electron microscope images, and you can find the difference between MgHA and Mg tin HA. So here it seems the particles what we are seeing here is a hydroxyapatite particles distribution. So here along with that we can also see the segregation of Mg to Sn phases and all these things. And yeah, we can see the EDS elemental mapping of MgHA surface. You can see the calcium and phosphates presence. So, and I mean that is from the hydroxyapatite we have added. So we can say that it is nicely distributed over the surface. And if we see the mechanical properties of all these three, pure magnesium and magnesium HA composite and magnesium tin HA composite. So obviously magnesium tin HA is showing a very good compressive strength and a good yield strength and fracture strain, low fracture strain, and yeah, elastic modulus is also improved. Okay, and hardness is also improved. So magnesium tin and HA are also proved to be good. And now let us consider this corrosion aspects of these three. So actually corrosion, if you see, as compared to the pure magnesium, actually it is deteriorated. That means magnesium HA is having very less corrosion resistance, but magnesium tin HA is improved slightly. It's better than pure magnesium and HA composite. So the addition of tin has definitely increased the corrosion resistance, but compared to magnesium, it is less. But yeah, it is but understandable, because the moment you make composites, definitely the corrosion resistance will definitely decrease. Um, so that's the thing. Okay, it's not alloying. Alloying will always improve the corrosion resistance, but the composites with the ceramic particles will definitely reduce the corrosion resistance. And of course, these are the parameters of electrochemical parameters which I showed earlier. So we can see clear the polarization resistance again, same thing. Magnesium is having good. The magnesium HA composites are least, and magnesium tin HA is better than magnesium in HA composite. So that's the conclusion of this study. And then we thought that we can actually try out with many elements. Okay, I've shown you earlier there are a lot of alloying elements which are being used along with the magnesium. Um, these are called nutrient elements. So these nutrient elements, each and every element has one good property. We have already understood that. So we thought of trying with multiple component alloy instead of only binary or ternary or quaternary. So to bring in various advantages into a particular, this biomaterial, and see whether we can use it and how good it is for the orthopedic implant applications. So we came up with the microalloyed and multi-component magnesium alloy and studied it. So we have added, so we named it as Magma 7. So 7 represents the 7 alloying elements, and magma represents magnesium microalloy. Okay, so the elements we have chosen is zinc, cerium, strontium, calcium, silver, manganese, silver, yeah, manganese, tin, and magnesium balance. So these are the alloying elements. So 1, 2, 3, 4, 5, 6, 7. So 7 alloying elements. That's why it's magma 7. So and this you see the chemical composition, the weight percentage of each element is very, very minimal. So that's why we call it as a microalloying, or uh, yeah. So the alloy, when you see, okay, when we prepared an alloy using casting route and see the optical microstructure, you can clearly, or this scanning electron microstructure, to see the surface morphology and microstructure. So you can see, you can clearly observe that there are almost no intermetallic compounds. So it's as good as a pure magnesium. You don't see any intermetallic compounds, or very, very minimal. Probably this, okay, here you can say that there is some intermetallic compounds, but it's so minimal that we couldn't find anything in the XRD pattern. And of course, this is mm, the tensile curve of this particular magma 7, and we got some ultimate tensile strength around 200. So it's a good having good this thing, and also we can see that ductility is also very good. That means we can see the plastic deformation region more, and we found that it is around 20% elongation. This particular alloy is having 20% elongation, which is very good, reasonably good. As I have told you already, the ductility can be improved by severe plastic deformation and also by alloying in some cases. So when we have alloyed with multiple components, multiple elements, so the ductility also increased, and we have minimalized the intermetallic compounds here. So that should also be the reason why it is showing a very good ductility. And yeah, these are the correlate characteristics of the same alloy. Okay, I have not compared, so but otherwise also it's showing a very good corrosion resistance. This is not a comparison graph, but it's the graph of only that particular alloy. You can see the TAFL here, and this is the Nyquist curve and the Bode curve, and this shows the pH during the pH variation during the corrosion process of magma 7. So initially the corrosion increases from 7.5 to around 8.5, and then slowly decreases again, comes back to 7.75 in around 170 hours. And yeah, so we could find out what is the corrosion rate. So it's low as 0.91 mm per year of this particular alloy. And when we check the bioactivity of the alloy, even the apatite formation is also very good. So we can clearly see a dense formation of the apatite layer. You can see um, the calcium here. Here the calcium, and this is phosphate. The presence of calcium and phosphate are very good, and other elements are magnesium and oxide that is also there. So along with that, calcium and phosphate presence also can be found. So that we can say that apatite formation is there. We have clearly indicated and marked here what are all the apatite particles and what is the magnesium hydroxide or something. So we can here also in the spectrum also you can clearly observe how much each percentage of element present in this thing. And we have also prepared magnesium-based high entropy alloys using the same elements, and we have calculated the basic calculation of basic thermodynamic empirical parameters for the high entropy alloys. So when we calculated this, then we have understood that delta S mix and delta H mix and these thermodynamic parameters. Okay, these parameters are very important to decide whether your alloy, this high entropy alloy, is going to form a solid solution or is going to have intermetallic compounds and so on. So, and the values which when we saw by calculating these things, we understood that it's going to have a solid solution formation. And we have casted it, then we have seen. Now this corresponds to the microalloy and that which we have discussed before, that is magma 7. And this graph, the pink one, refers to high entropy alloy. So, and surprisingly, we have seen multiple and complex intermetallic compounds where we have expected solid solution formation, but we found so many complex intermetallic compounds we listed out here. So calcium CaZn5, Ca2SN, and beta manganese, of course, and Ce6Mg23 and Sn. So these are all the complex intermetallic compounds which we find in high entropy alloy. And this you can here clearly see the scanning electron microscope micrographs of the microstructure of both microalloy and HEA. It's very obvious that here in microalloy there are no intermetallic compounds at all, and whereas in HEA it's segregated along the grain boundaries. Lots of intermetallic compounds are present, which we have already seen in the XRD. And corrosion studies, when we compare to, of course, this graph represents even the quoted ones also, but I'm not going to discuss now. But when you compare microalloy and high entropy alloys here, the blue one corresponds to microalloy, and the HEA correspond to the black gray color correspond to high entropy alloy. So these two are the uncoated alloys. One is microalloy and another one is high entropy alloy. If you look at the corrosion rates, obviously microalloy is performing much better compared to high entropy alloy in terms of corrosion. It shows slightly lesser corrosion resistance. High entropy alloy shows a little bit less corrosion resistance compared to the microalloy. So that's again obvious. It is probably due to the intermetallic high amount of intermetallic phases present. So the galvanic coupling can happen. So because of that, probably HEA shows less corrosion resistance. And we also did the cell viability test between all these things. So if you see here, this is the high entropy alloy, this is the micro alloy, and these are the coated ones. Of course, I'll discuss that coating a little later, but we can see clearly that both HEA and MA, the cell viability is good, and compared to HEA, microalloy is even better in terms of cell viability. Of course, these coated ones are even better than the bare alloys. That we can conclude that actually the coating has the what coating it is. I'll discuss that later. But the coating has given definitely uh, uh, helped in improving the cell viability. So, and among microalloy and HEA, that is HEA refers to high entropy alloy. Microalloy shows a reasonably good cell viability. And yeah, I have also discussed that severe plastic deformation improves the ductility and room temperature formability. So I have also researched in using friction stir processing to develop surface composites and surface alloys. So one of the work I'm presenting here briefly, that is I worked on ZK60 magnesium alloy, and I have developed a bioactive surface by inducing various elements, including hydroxyapatite. I'm going to present here about hydroxyapatite now, but I have also prepared surface composites using various ceramics, and even prepared surface alloys using various elements, metallic elements. So I have to prepare this, I have made holes and filled them with the hydroxyapatite or whatever the reinforcement we want to make, and then use these parameters to, for the friction stir processing. So then we have done the friction stir processing, and then we observed that uh, this refers to that HA composite surface composite prepared by inducing HA onto the surface on ZK60 magnesium alloy. So, and we found that there are two phases. One is alpha magnesium, that is the matrix, and intermetallic compound magnesium zinc. Okay, so this is what we found in the XRD. So of course, we can see the microstructure before friction stir processing and after friction stir processing. So large reduction in we can see the large reduction in the grain size. Okay, and this is the a junction between the FS speed area, and this is the base. And in between, you can clearly see that this is the stir zone, and here it is thermomechanical affected zone, and this is heat affected zone. We can see the three zones very clearly here, and bioactivity of this particular uh, surface composite of ZK60. If you see, we can clearly beautifully see that we can the formation of apatite here, nice pearl-like formation here, you can see. So the calcium and phosphate presence is also very good. So this magnesium uh, the light appears here like that. Okay, that exactly the location is here. That means this coating, it has formed like a coating. So underneath that, the substrate is there. So that substrate is only here, it's showing. So in the coating, we have very less magnesium and zinc, but the content of zirconium is high. Content of calcium and phosphates are high, and oxygen also high. So we can say that the phases formed here are magnesium oxide or magnesium hydroxide, and along with that, we also can find calcium, and phosphates. So that we can say that it has a good bioactivity. It's improved. It has the bioactivity has improved. Now we'll discuss about surface modification processes to improve the corrosion resistance and improve the bioactivity and so on. So if you look at the surface modification processes, we have two varieties of surface modifications. One is physical modification on the left side, and another one is a chemical surface modification. So surface modification, when you see the technologies are like plasma spraying technology, plasma immersion ion implantation, and plasma immersion ion implantation and deposition technique, and physical vapor deposition techniques. These are some of the famous physical modification techniques we have. Every uh, every modification, surface modification technique has some advantage, and of course they do has disadvantages. Every process has definitely disadvantages by itself. So we cannot say this process is particularly good and this process is particularly bad, but it all depends on uh, the application. Okay, so everything has advantages and disadvantages. And if you see chemical modification side, we have chemical vapor deposition and sol gel method, and other one is micro arc oxidation, or also called as plasma electrolytic oxidation. So, and other way of categorizing these coating techniques is one is the deposition type of processes, that is coating is deposited, and another category is conversion coatings. Okay, some of the coatings are converted coatings. That means the surface itself will get converted in, like its own surface will get converted to its oxide or something. So that is called conversion type of coating. So if you look at and compare all these processes, whether it is CVD or PVD, and all these techniques, and even the plasma spraying technology, all comes under deposition type of coatings. And this micro arc oxidation is something which is it's a conversion type of coating. Okay, it's a electrolytic process. So the surface will get converted into its oxides. So the main advantage comes when you go for conversion coatings is the peel off. Okay, so you will have a very good uh, uh, the adhesion strength of the coating. So when you go for the deposition type of coatings like PVD, CVD, over the period of time, you will see that the coating has faded off or damaged. But when you see these converted coating processes, the adhesion of this coating is so high because its own surface has got converted. So there is no question of poor adhesion or something. So it will have very good adhesion strength. And of course, and micro arc oxidation or plasma electrolytic oxidation has some more advantages that because the coating which formed by this process is a hard ceramic coating. Uh, like for example, if you do the process this process on magnesium, it will develop magnesium oxide coating. And if you do it on aluminum, it will become aluminum oxide coating, and so on. And this process can be used only for some metals like aluminum, magnesium, and titanium, tantalum. This kind of all materials only can be used. That is the only kind of limitation. Other metals cannot be used. Uh, but for these materials, it's a very good process to produce a corrosion resistant and highly wear resistant coating. And yeah, you can see a short video how this plasma electrolytic oxidation process works. So what you're seeing here is the arcing is happening on the surface. Okay, so each arc we call it as a plasma, And that's why the name is plasma electrolytic oxidation, and it is an electrolytic process. So the workpiece here is our anode. Okay, the workpiece here, you can see what is the workpiece you are seeing is an anode, and the cathode can be the stainless steel. And electrolyte contains a very basic alkaline electrolytes, so very eco-friendly. So simple sodium silicate and potassium hydroxide, this kind of alkaline salts. So it's very eco-friendly process, but of course the disadvantage is high energy consuming process. But otherwise, it's a very good coating process to get a very good hard ceramic coating for various applications. You can say that various uh, I have I've done some coatings here. You can also see the above one which you are seeing is uh, the piston. Okay, aluminum piston. So on the aluminum piston crown, I have given a coating. So this is uncoated one, and this is the coated one. And similarly, this is the aluminum watch dial. Okay, so the uncoated one and then coated one, just to improve. This will improve the corrosion resistance and wear resistance also. And later on, we have done the tests of engine tests on these aluminum piston cups. So it has endured the combustion and the heat. So we could save the cup here. Okay, so this is a very good application for this kind of process. And how it works is basically, so first the first phase is the formation of discrete discharge channels, and then later on the ejection of oxide from substrate, and finally quenching the ejected material. So when you apply the voltage across the terminals, anode and cathode, actually what happens is this: first a passive film will form, that is a natural passive film, and over the period of time, the porous oxide film will generate, and then beyond some certain voltage, you will start seeing the sparking or arcing on the surface of this particular material. Then that's when actually what is happening is the dielectric breakdown of this passive film happens, and then it will start arcing. The surface will start to arcing, and then this continues, and until the whole surface is covered with the oxide, this arcing happens, and finally you will end up having a uniform coating on the surface. So this is the steps by sorry these are the steps. So this is the growth of porous oxide, and then dielectric breakdown, and then this each channel of the when once the arcing starts, then we consider this each channel as a plasma channel where actually the reaction happens. So magnesium, our material is substrate is magnesium, then magnesium ions will release Mg2 plus, and then from the surrounding electrolyte we have OH minus ions present. So magnesium 2 plus and OH minus will react and form magnesium oxide because it's a high temperature. So immediately magnesium oxide will form. This molten oxide will evolve like you can see like a volcano how it erupts. So the same way the magnesium oxide will form, and immediately it will get quenched because of the surrounding cool electrolyte. So electrolyte being cool is very important here. So for the better coating and better properties in the coating also. So it will get settled down. This finally magnesium oxide will get settled down on the surface. So finally you will have a thick and densified coating here. So the process continues until wherever the substrate is exposed. So from there the arc try to generate, and then at that place the magnesium oxide will form, and finally it will cover up the surface. So once that this is over, this process where you don't see any substrate. So until then, the process keeps going, and then finally a dense coating will form, and it will automatically stop. The process will stop. So typical time of the coating process, you can say that it is around 10 minutes. It can sometimes go up to 20 minutes too, depending on the current and voltage. So when we talk about this, the process parameters of this particular process, there are two main factors. One is the electrolyte, and another one is electrical parameter. So electrolyte also affects the coating, the characteristics of the coating, the what type of electrolyte we have used. That is, what is the chemistry of electrolytes we have used, what is the concentration of electrolyte we have used, and so on, and what is the pH of the electrolyte we have used, and conductivity of the electrolyte, temperature of the electrolyte. All these will influence the your coating. And the electrical parameters, on the other hand, if you see the current and voltage what we have applied, and of course this process can be done in two ways. One is at a constant current, and another one is at constant voltage. Either way you can do. But most widely used method is to do this coating. The sorry, constant current, to use the constant current mode. Okay, so anyway, so this current voltage, all these things will affect the coating parameter, coating characteristics, and whether we are using a pure DC and pulsed DC, that also matters, and unipolar or bipolar, or whether it is DC or AC, that also matters, and pulse frequency and duty cycles. All these things, electrical parameters, will affect the coating. For example, if you see, when you increase the current, always the increasing current or high currents will produce a lot of heat, will generate a lot of heat. So electrolyte will start to boil, and you need to have a sophisticated mechanism to cool it down. See, otherwise, once the electrolyte starts to boil, or the coating gets damaged, and so on. So each and everything will have its effect on the coating. Okay, and finally the process time, how much time you do. So of course, more the process time directly affects the thickness of the coating. The more time you do, the more thickness it can grow. So these are all the PAO process parameters. So I have developed using this technology. I have developed hydroxyapatite induced coating. Okay, so I have coated the hydroxyapatite on the ZM21 magnesium alloy using this technique. So I could successfully develop. So these are the electrolyte solution I have used. Okay, sodium phosphate and potassium hydroxide, and I have added hydroxyapatite powder and of course triethanolamine to charge these powders. So the mechanism was to, during the formation of the magnesium oxide, the hydroxyapatites particles also, which are there in the electrolyte, will also get attracted to, or electrophoretically dragged onto the surface of my alloy ZM21, so, and gets embedded in the magnesium oxide matrix. So for that purpose only, I have added a triethanolamine to charge these particles, hydroxyapatite particles, and of course ethylene glycol I have used to use the suspension stability, to increase the suspension stability, because when we add hydroxyapatite, this is not it is not dissolvable in the water, so it forms a suspension. So I need a suspension stability. I should not allow these particles to go down and settle down as long as the process is going on. And of course, as I told you, we generally use the constant current mode, and the constant current which I have used is 1.5 amps, and frequency I set it at 50 hertz. Duty cycle is 90% because it's a pulsed DC. Duty cycle, that means on time is 90, off time is 10%. and process time is just 5 minutes, and final voltage was 550. So this is the after doing this experiment, I have checked the XRD, and we found that very clearly. You can see in the inset here, smaller this one, there's a HA peak here very clearly. So that means HA has successfully come onto the surface of magnesium oxide. I mean, it got embedded in the magnesium oxide when I tried this ZM21 on the PEO using PEO. So successfully, I can say that oxide and hydroxide grade composite has been formed. So of course, this is how the surface morphology looks like. So all these are pores, but not open to the substrate. Maybe interconnected pores it can be. And this is the pure PEO coating. And if you see oxide plus HA, hydroxide induced coating, you can see even the pores are also closed. So that means if by adding hydroxide, you can also seal the pores, and the thickness also increased, coating thickness also increased, and of course even the corrosion resistance also increased, obviously because the pores are getting reduced, so even the corrosion resistance also increases. So this is what I have concluded from that study. I've done also have actually not only on ZM21, I have used AZ31 also. I have studied on AZ31, and I have done this cell adhesion test also. Of course, we can see clearly the cells also adhered and proliferation also is there, spread. Okay, so that means the surface is good compared to the substrate. Okay, the coated and along with HAFU coat, definitely the cell adhesion has increased. And this is the recent study to incorporate spirulina, which is hopefully everyone knows about spirulina. Okay, spirulina is very good for good for many uh, health issues actually. So we will take that as a drink. It's a algae, you know it. So we have thought that maybe this can improve the bioactivity and probably uh, characteristic like antibacterial ability and all those things. So we have incorporated spirulina, just how we have incorporated hydroxyapatite into these coatings. We have tried to incorporate spirulina, and of course, yes, it has given us very good results. So you can see in the XRD, you can clearly see the spirulina peaks, and yeah, by incorporating the spirulina, you can see the contact angle has reduced. That means hydrophilic surface has been created, which is very good for a biomaterial. And of course, yeah, the biomineralization also is very good. Okay, so you can see that. So I'm rushing through the slides now because I think time is running short of time. So of course, the TAFL plots, if you see, even the corrosion resistance also is very good. Okay, and similarly, we have added Bredigate coating. Okay, this Bredigate is also one of the bioactive ceramic compared to, I mean, as like hydroxyapatite. This is also calcium silicate uh, ceramic. So we tried with this, and this also yielded very good results. So it is even more hydrophilic with 18.6 degrees, and we have successfully incorporated Bredigate into the PEO coating, and yeah, see, you can very clearly see the biomineralization here. So very beautifully formed peptides, you can clearly see. And yeah, even cell viability, when you see, Bredigate is showing a very good cell viability in every dilution. Okay, see here. Okay, this BG refers to the Bredigate. So, and of course in the bar charts also it's very, very clear. So it is having high cell viability percentage. So with this, I came to the conclusion of my presentation. So generally, this is how the research on biomaterials goes on. So we study the bulk surface and biological attributes of biomaterials at the initial level, and then we'll apply the engineering to develop biomedical implant, and then do we study the in vitro and in vivo, and then clinical testings it has to undergo. And once it is proved in vitro and in vivo, then regulatory approvals will go for regulatory approvals, and then finally we can commercialize for the clinical applications. So this is the path from the fundamental study of the biomaterial to the commercialization, complete final clinical applications. So thank you very much. Now the forum is open for question and answers. If you have any questions, I'll be very happy to answer. Thank you very much.
Thank you, sir. Very wonderful presentation.
Thank you.
I would request the participants, please unmute yourself and you can ask the doubts that you have. Sir will clarify the doubts.
Good afternoon, sir.
Good afternoon.
Sir, which SBF you use, sir, for that testing? You have already
SBF.
that mentioned. SBF, yes, sir.
Oh, Cocobos SPF, yeah.
What, sir?
Cocobo solution. There is a standard Cocobo solution. We call it as Cocobo.
Cocobo, sir.
Yes, Kokob.
Okay, sir.
I mean, you can just Google it, you'll find it. That's a standard SBF preparation, very well known, and it has a particular way of preparing. We have a particular components in that SBF, and so we have to prepare in a particular the exactly how it was mentioned. There is a paper on that. There's a publication in which he clearly explained what are the steps to be followed, how to prepare SBF, how to store SBF. So you have to follow the same steps. Then you can do the test in that. Of course, SPF is one of the media in which we generally test this bioactivity or any all these things. Apart from that, you can also go for ringer solution and the DMEM.
Ringer or
So many.
resin, sir? Can I also?
Which one?
Resin. That.
Which resin?
That SBS also coming, sir.
I'm not getting you. Sorry.
I think SBF also is coming in that form of resin, sir.
Mm-hmm. No.
No, sir. Okay.
No.
Sir, excuse me, one question.
Yes.
Magnesium is an absorbing material, sir, or
yeah,
it can be it's absorbed, no?
Yes.
During
Biodegradable. Yes, degradable material.
Okay.
And we are giving the coating. I have presented here about plasma electrolytic oxidation coating to reduce the corrosion rates, not to completely arrest the corrosion, because we ultimately need the biodegradable implant, not a permanent implant. Okay, so I want the degradability, but I just wanted to reduce the corrosion rates. That's it. Because if it is too high corrosion rate, what happens is the hydrogen emulsion is a big problem, and then it can also be too toxic, so to the body. So that's why we need to reduce the corrosion rates, but we should not arrest completely, because ultimately we are talking about biodegradable implants.
Okay, thank you, sir.
Excuse me, sir.
Yes.
After the coating of hydroxypeptide, sir.
Yeah.
Can you check that corrosion resistance over that substrate? It will increase or decrease after that coating, because.
Yes, I have presented, right? Definitely the corrosion rate completely increases. It's highly increasing. Yeah.
So corrosion rate if increase, sir.
Sorry, I mean to say, did I say corrosion rate? corrosion resistance increases, corrosion
Okay, and
rate
that
decreases.
have you also go through the VR test, sir?
Yeah, VR test I have not presented, but we have done in a couple of times because actual for biomedical application, the VR test what you need to do is a tribo corrosion test actually.
Yes, sir. Yes,
So,
sir.
yeah, that is more important than doing a simple wear test.
So did you go through that one, sir?
Yes, yes, yes. In that also performance was very good, but I haven't presented here the results, but I have checked. Yes,
Means it is decreasing, sir, or increasing?
definitely, definitely. The performance in tribo corrosion is very good.
Okay, sir.
So because of the coating, after coating, especially I'm telling you, it's not without coating. The coating has improved the tribological properties as well as corrosion properties.
Okay. Thank you, sir.
Yeah.
Dear participants, any more questions?
Uh, sir,
Yes, yes.
you did that tribo test after the that workpiece submerged in that SBF or without in the dry, or you did that?
No. In the SPF only you have to do. Yes.
Okay, because all the test corrosion, all this thing tested under the
Yes.
SBF.
Oh, yeah, correct.
Yes, sir. I also want to ask you, sir. Did you, sir, check that antibacterial test after that coating, sir, or only you
Yes.
go through that cell adhesion?
No. We do cell viability, cell adhesion, and then antibacterial. Okay, and antibacterial, yes, I have done for few, and some of them has shown not much of antibacterial properties, and some of the coatings have shown very good antibacterial properties. Yes, I have done. Yeah,
So which
so
cell cell
it depends on the uh, this one. Okay.
which cell you use, sir, for that cell attachment?
MGT.
MG63, sir.
Yes, 63. Yes.
So how can you identify, sir? Suppose I am a new researcher, sir. So how can you identify that which cell is good for me? How to select that which cell is good for testing? There are so many cells are there. There's
Yes.
MC63, MC3T3.
Yes.
So how to
Yes,
select that
yeah,
one?
yeah, yeah. There is no such thing. It depends on the application actually. The for most of the orthopedic applications, we'll either go for osteoblast cells and or this MGT63. Okay. So, but of course, that's what research they do. They try with many other things. But I don't think that uh, we need to find exactly which cells are more apt to test for the particular
Yeah,
application,
yes, sir. Yes,
and
sir.
based on that we need to do.
Suppose
So
I want to
it's
do that orthopedic implantation. Suppose that I hip implantation. So in that case, which cell I choose? So that's why my question. Suppose
I
I'm
think
going
that
to for.
yes, MGT 63. I would prefer MGT 63.
Okay,
So
sir.
that would be fine.
Thank you, sir.
Yeah.
Thank you, sir. Thank you so
Okay.
much for the presentation.
Yeah. Once again, I thank you very much, and I thank everyone present here and for their patient listening to my presentation. And thanks once again the organizers for giving me this opportunity
Excuse me, sir.
to present. Yeah. I
Can you
think
give the
questions have
contact
not
number, sir? Your any
content. Sorry.
contact, yeah, email ID or your contact number like that, sir.
Yeah. I
So that
think.
future I can.
Sure. I think you can contact the coordinator, Mr. Ajay. I think he'll be able to provide you.
Okay, sir. Okay.
Yeah. If I can even share the slides. That's not a problem. So anyone wants to work with me in collaboration for the research, you're most welcome. We can have the collaboration and work.
Okay, sir.
उसमें ये वो केबल का प्रॉब्लम था, चिप चल नहीं रहा था.
Okay. So I think we are done here. I once again thank the coordinators. I was thanking actually for giving this opportunity to present here. I think if I have taken too much time. I'm very sorry. I think next presenter must be waiting. So.
But it's informative, sir.
Thank you so much. Thank you.
Thank you, sir.
Thank you all. Thank you. I can leave now?
Yes, sir.
Okay. Thank you.
Requesting the participants to join for the second session on day 6 of FDP titled Advanced Biomaterials for Orthopedic and Tissue Engineering Applications. Due to some last minute changes of resource persons, today the second session will be handled by the co-coordinator of this FDP, Mr. V. Venkatesh.
Good afternoon, my dear participants. Good afternoon, my dear participants. I think you are very well know about me because from past 5 to 6 days we are in contact with each other through call or through our WhatsApp groups. Due to some technical issues, the schedule, there is a minor change in the schedule. And in this, this session will be handled by me. In this session, I will be discussing about the major steps that I had taken in publishing one paper, which is titled as Silk Fibron Infilled 3D Printed Polymer Composite Scaffold to Enhance Cell Adhesion and Cell Viability. So before start my talk, I would like to thank Charles Hall, who is father of additive manufacturing technology. Earlier it is called as 3D printing or rapid prototyping. And many of the participants were very new to this environment. So for the sake of this reason, I would like to explain you the number of steps in development of any product by using any kind of additive manufacturing technology. And this protocol is common for all varieties of additive manufacturing technologies. So if you wanted to develop any physical product by using any kind of additive manufacturing technology, first a CAD model is required. Then this CAD model has to be converted into the STL format, which is also called as stereolithography file. And some other cases, it will be called as a standardization language. And this file has to be transferred to the software which is provided by the manufacturer of the particular additive manufacturing technology. After that, it produces the G codes. After that, the fifth step includes the building of the part, and sixth step includes after completion of product development, it has to be detached from the build plate of the additive manufacturing setup, and we have to apply different types of post-processing setups. Number and types of post-processing setups were purely connected to the type of additive manufacturing technology which we use to develop the product. And the last step is the use of the final product in final applications. And majority of the additive manufacturing technologies are nowadays used in the applications. And in olden days, this technology is termed as rapid prototyping. Means these technologies were developed for the sake of producing the prototypes, but due to development in material aspect, technology aspect, and other developments in other aspects, so the final product accuracy is equal to the near net shape component. So that's why the final product was nowadays used in the final applications. So here I would like to list out the classifications of 3D printing technologies or processes. So these classifications were generated as per my perspective. And coming to the first classification, which is called as a wet photopolymerization, where the raw material is in the form of a liquid, nothing but photopolymer. So by processing the photopolymer in different ways, by exposing the photopolymer in different ways of the light sources, we can develop the product. So majority of the 3D printing technologies were classified into wet photopolymerization, where 5 different technologies were available. And next variety of technology is material extrusion based or wipe based technology, where the material is extruded either by using hydraulic energy or screw extrusion or pneumatic energy or the mechanical energy. In this category, there are nearly 5 different varieties of technologies. Coming to the third classification, this classification consisting of material which is in a form of liquid, but here the material exposes to a particular type of light, so where the final product will be developed with a very good surface finish. And the fourth one consisting of only one technology, where it is termed as binder jetting technology, where the material is in the form of powder. By applying a thin layer of the binder, the final product will be produced. And coming to the fifth classification, where the material is in the form of powder. Powder is exposed to at very high temperature with the help of the laser. So that's why it is called as a powder bed fusion. The fused powder gets the fused powder get attached or binded with the surrounding particles, so that the final product will be developed. And sixth one is over here the raw material is also in the form of powder, but selectively it will be sintered at very high temperature to
Yeah,
develop
excuse me, sir.
sir.
Your slide is not moving, sir.
Okay, now
No, sir. Now,
now
now,
is it okay,
now,
sir?
now that classification of 3D printing process. On that slide you are there.
Yes, yes sir, yes sir. I'm at slide number 5 right now.
So
Okay, sir.
can I put in the presentation mode, sir? Can I put the your PPT?
No, that's what due to some technical reasons it was unable to change. So here I'm trying to change my slides. Are you able to see the change slides? Chittaranjan sir?
No, sir. No, sir.
Okay, then I will do one thing. I will exit from the slide
And I
presentation
can
mode and
rejoin, sir, and maybe it will be sorted.
sir, pardon sir.
Yeah, sir. Rejoin. Maybe problem will sort.
It's okay, sir. Now I think the slides are visible to you, right, sir?
Yeah, sir. Visible that class
Okay.
that fourth slide.
Ha. Okay.
Now
The seventh
it's
classification consisting of seventh classification is termed as a sheet lamination technology, where the material is in the form of sheet. It may be a paper sheet or a composite sheet, or it may be a polymer sheet. And the title of the eighth classification is digital light processing, where the digital light is, especially the UV light, is exposed to the photopolymer. And the ninth variety is very popular and advanced technology, which is called as bioprinting. And tenth one is also one of the recently developed technology, which is called as FRESH. Its full form is free form reversible embedded of suspended hydrogen. And last but one is 4D printing. After completion of developing the product with respect to external parameters like pressure, temperature, humidity, and some other reasons, the shape, size, and behavior of the final product gets changes. Chittaranjan sir, if you don't mind, will you please mute your mic? Okay. Now the last classification is titled as food printing. So here in this presentation, I would like to discuss the major technologies which are useful for the academicians especially. So the first technology is familiar to everyone, which is termed as fused deposition modeling. Uh, the advantages of the fused deposition modeling technology is very well known to us. So here we can able to develop the functional products, and remember that this technology is suitable to produce polymer products only, and this technology is not at all suitable to produce product with a metal or composite materials. But for little composite materials, it's possible, not for the R varieties. And the wastage in this technology is very minimal, and it's very simple to remove the support structures. At the same time, it's very simple to change the materials after completion of building one particular product. And coming to the major disadvantages, instead of disadvantages, I can say it as a limitation. So the accuracy of the products produced by using this technology is very limited. And this technology products produced with this technology were used in multiple applications. And coming to the materials which are suitable in this technology are composite, not all varieties of composite, limited varieties of composite materials, ABS, PLA, nylon, PETG, and some other varieties. The other technology is termed as a pneumatic extrusion or multimatic extrusion, which is a part of bioprinting, where the polymer material is used to extrude under the presence of pneumatic energy, even at room temperature or the temperature which is greater than the room temperature. And here you can see the schematic representation of pneumatic extrusion or multimatic extrusion based technology, where you can find two different nozzles. These two are used to handle two different materials. And coming to the advantages, this technology is used to fabricate organs, human bodies, bones, scaffolds, so I mean patches, skin patches or wound patches and some other things. And the major advantage, the other advantage of this technology is you can play majority of the materials with this technology. And coming to the types of materials suitable in this technology, it's bioinks, hydrogel, all types of polymer composites and polymers as well. So the other variety of technology is laminated object manufacturing, as I mentioned to you in the classification in the beginning of my presentation. In this technology, the material is in the form of sheet. So this material may be a paper material or the composite paper or a plastic paper, polymer paper. And the final product were very used in fit, form and functional applications. So whereas if you wanted to develop any product with transparent materials, which is used for sharing your ideas, sharing the thoughts, sharing your opinions to the clients or the customers or the end users, so you can take the advantage of this technology, because the surface finish of this particular technology is excellent compared to all varieties of additive manufacturing technologies till now. And name of this technology is polyjet printing. And here, the major limitation with this technology is it's not so. This technology is not suitable for our varieties of materials. The one which is provided by the manufacturer, we can take the advantage of those materials to take this technology to develop the products. And the next variety of technology is bioprinting, where three different types of processes were involved. The first one is extrusion-based. The second one is inkjet-based bioprinting, and third one is laser-assisted-based bioprinting. And here we can use different types of materials, whether it may be in the form of liquid or gel or composite or paste or polymer and some other things. So when it comes to a new technology which is termed as coaxial bioprinting, so here the previous technologies were dedicated to use one material at a time, at a single step. But in these technologies, in a single extrusion, we can combine two different materials. If you just imagine, if two circles were drawn, if we draw two circles which are concentrated with each other, so then it will be called as a coaxial arrangement over here. And if you draw three circles, three concentric circles with the different diameters, then it will be called as a triaxial bioprinting. So in coaxial printing, there are two nozzles. The inner nozzle is termed as core. The outer nozzle is termed as shell. So you can extrude two different materials from these two different varieties of nozzles in fabrications of arteries, vessels, nerves, and some other things. So a few years back, nearly 3 to 4 years back, one researcher developed a new technology in 3D printing, which is used for biomedical application, which is termed as FRESH. Its full form is free form reversible embedding of suspended shells. So here, without support structure, you will be printing the final material or final product within a gel, a bath of gel. After that, when you heat the entire platform or the entire petri dish up to a particular temperature where the supporting gel gets melted, so you will get the final product. And here, nearly 1 or 2 years back, the other researcher proposed one more method, which is called as modified fresh technology. So here, the material which is printed in the support structure gets melted. In the earlier case, the support structure material gets melted after completion of printing, but here the material which is melted, which is printed within the support structure gets melted. With this, it's possible to develop fine channels which are used for multiple applications. And the last variety of technology is called as 4D printing. So last part one, I'm sorry. So where after completion of product development with respect to the external parameters of the product atmosphere like temperature, pressure, humidity, moisture, and some other details, I mean forces which are applying on that, the behavior of the product gets changes. And the last technology is very, very familiar to us, which is called as food printing technology. So here, from past 2 to 3 years, majority of the researchers are working in the development of customized food products with the different materials. And I forgot to cover one more technology over here. It is also called as concrete printing technology, where civil engineers and different types of engineers we're taking advantage of this technology to produce highly complex structures at very less time. And Chittaranjan sir, if you remember, long back, IIT Madras has developed our country's first 3D printed house, I think so, in IIT Madras campus. So whatever the knowledge that I gained with above classifications or with above technology, I wanted to develop a setup which meets my requirement, but due to some limitations, I could not able to move forward. But I thought that uh, with the available resources which are available in the institute, we can able to develop extrusion-based technologies. In this connection, every one of you know that the photograph shows a simple vertical milling machine. So as we know that milling machine is considered into subtractive manufacturing process, where the material gets removed layer by layer or in one particular direction to get the final product. The removed material is called as chips. So, but I converted the subtractive additive manufacturing mission, subtractive CNC milling mission into an additive mission. So, by manipulating a few things in the controller and by developing a Z code, our customized Z code, I converted the subtractive mission into additive manufacturing mission. So here I took the advantage of pneumatic energy, and I started to extrude the paste, which is combination of polycaprolactam and beta-calcium phosphate, as well as the solvent here we used as the chloroform. And we can able to print not only the paste kind of material. I converted the simple milling machine into metal melt extrusion based additive manufacturing technology, where the melted polymer gets extruded from the heated barrel by applying the pneumatic energy. The heated polymer started to extrude from a fine diameter of the nozzle. And here you can see few samples which I printed with the help of the modified CNC simple vertical milling machine. And with this inspiration, I did so much literature in development of customized, I mean, my own pneumatic or melt pneumatic extrusion based setup. So I verified so many international papers, and majority of the researchers used screw-based extrusion technology. So where they used agar screws or a customized screw to extrude polymer materials which were melted at very high temperatures. So I found there are so many limitations and difficulties uh, in these architectures or setups. So to overcome these technologies, I proposed the limitations, the list of limitations which were identified in my literature. These are the following limitations which I identified. So the first limitation is material compatibility. The above mentioned technologies or the above published technologies were not suitable for all varieties of materials, including polymers or polymer composites or hydrosols and some other. And the extrusion is a vast. There is no precise extrusion. There is no precise extrusion control over the extrusion nozzle, and clogging issues that was identified with the above setups. Speed and throughput also one of the major limitation in development of the products made by the different researchers, and the wastage of materials was also very high. And the sixth limitation is complexity of the setup. There are so many number of moving components, and it's quite difficult to control. At the same time, the proposed technologies were not in a position to print complex and multi-material products. And the last limitation which I identified is limited to material range. I mean, few materials were possible to use in the our technologies which were published by different researchers. And instead of screw extrusion, I would like to propose pneumatic extrusion based technology with that you can find out the following technologies. One is material diversity. This technology is suitable for vast varieties of materials like hydrogens, paste, polymers, polymer composites, and some other. But the major limitation with this technology is it's not possible to print any metal product with this technology. And and with the above limit, I mean, by resolving the above limitations, I propose to one system where the specifications of the proposed system were very limited, very similar to the international brands which are available in the market. And with this inspiration, I wanted to work out on development of bone scaffolds, which are used to resolve different problems caused due to the formation of trauma, accident, infections, surgical resections are due to bone defects at different regions like at neck region, at head region, jaw regions, either soft or hard tissue damages, especially in maxillofacial regions. And we have very limited number of methods to overcome above mentioned problems. One is autologous, second one is allogenic, third one is exograft, fourth one is implant, and the last one is bone tissue engineering, I mean, tissue engineering bone grafts. So here I would like to concentrate majorly on tissue engineering bone grafts to overcome different problems where the patients faces. And in development of tissue engineering bone grafts, we have majorly four different varieties of materials. One is metals, second one is polymers, third one is ceramics, and last one is the composites. So here, my work is majorly concentrated on the development of the bone scaffold by using one of the additive manufacturing technology, which is called as melt pneumatic extrusion. And the material over here is, which I use over here, is a polymer composite. And we have alternative methods to fabricate the bone scaffolds. So they are called as traditionally manufacturing methods. So they were termed as a salt leaching method, ice particle leaching method, gas forming method, freeze drying method, and the tips. But there are so many limitations with traditionally manufacturing bone scaffolds. So the first one is it's not possible to control the pore shape, size, and interconnectivity. And the porosity is also not possible to control with the traditional bone scaffold fabrication techniques. And the last one is the compatibility of materials. So these five methods were not compatible with all varieties of materials. Anyway, these are the limitations that I identified with the traditional technologies. To overcome all these things, I moved to advanced 3D printing technology, which is called as pneumatic-based extrusion or melt pneumatic-based extrusion. So anyway, I got some idea to develop bone scaffolds, and I am trying to develop my own extrusion-based system to develop the bone scaffolds. But I'm unable to identify the material which is used to fabricate the bone scaffolds. In my literature, I could identify polycaprolactam as the best material to fabricate the bone scaffolds. So not only the pure polymer, my system is in a position to able to print polymer composites as well. So there are so many properties to the polycaprolactone material. So it melts at very less temperature, that is nothing but a low melting point, and it has a kind of nature which is called as hydrophobic. By reacting, I mean by following a particular protocol, we can convert the surface of polycaprolactone from hydrophobic to hydrophilic. And as Sreekanth sir discussed, so polycaprolactone can be used as a suture materials, which can be degraded into the human body after some time. And this particular material was used in so many applications in biomedical. So like in fabrication of the implants and fabrication of bone tissue engineering components, I mean products, and tissue repairs are tissue engineering, wound healing applications, I mean one in fabrication of wound patches, drug delivery systems, in fabrication of sutures. Likewise, there are so many applications where the polycaprolactone has been used. So with this information, I would like to uh, work out my further research on polycaprolactone as the base material. So with this inspiration and with this groundwork, I developed my own pneumatic and extrusion-based technology. And in the year 2023, we published one paper which is titled as a silk fibrin infilled 3D printed polymer composite scaffolds to enhance cell adhesion and cell biobiology. And this is about the geometric model we prepared before we start printing it. As I mentioned you in the beginning of the slide, so there are totally 8 number of steps in development of any product by using any type of additive manufacturing technology. We follow the same procedure to fabricate the bone scaffolds, and here we nearly fabricated 3 different varieties of bone scaffolds. One is the pure polycaprolactone, and the second one is combination of polycaprolactone, hydroxyapatite, and magnesium oxide. And the third one is a combination of again polycaprolactone, hydroxyapatite, magnesium oxide, and silk fiber. And we started to compare. This particular slide will give you the details of 3D printed struts with the different materials, and we did in vitro analysis on the printed samples with with 3 different materials. One is pure PCL, and the second one is PCL composite, PCL hydroxyapatite and magnesium oxide. And third sample is silk fibrin based PCL composites. So we did in vitro analysis and mechanical XRD analysis, some analysis and mechanical properties of it. So we could say that the cell viability of the silk fibrin based PCL composite scaffolds has been improved a lot compared to first 2 varieties of scaffolds which were fabricated by using PCL and PCL composite. And this is about the conclusion of my work. So not only this, uh, this is what we did up to the year 2023, and after that, I developed my own Python program to prepare different architectures with the setup which I developed at our institute. So with this setup, you can able to develop the products by using geometric entities. I mean, if you give the coordinates of the geometry to my Python program, I mean the one which I developed, it can able to develop the Z code for you. If you share this G code to the a setup we developed at our institute, it's straight away develop the final products. And the second method is development of different products like two-dimensional geometries, or helix continuous printing, or many of the mechanical engineers were known about Bezier and B-spline, and our technology is in a position to print 3-dimensional Beziers in a support structure. So with this, this second image will shows you that will tells you that whatever the Python programs we developed with the different mathematical equations, they propose to, the developed setup is in a position to print any complex material with any material. Sorry, any complex shapes with any materials. So here we used pluronic F127 as the material to print these structures. And coming to the third variety of input, it is very well known to us. If you have a CAD model with you, and our system is in a position to support to print any complex geometries from the CAD model. And not only that, we developed our Python programming scripts to do manipulations of different geometries, like reproducing the similar geometries. And second manipulation is we developed a Python program to connect two different lines and whatever the curvature that you are observing. So this was the Z code developed by the Python program we developed our institute. So likewise, we started to work in doing so many things with the proposal system. And in very recently, we started to work out on the development of wool patches by using chitosan material. As we know that chitosan is naturally extracted material from the sea base, we can able to produce it, and the chitosan was used in so many applications. Like in the development of micro or nano fibers, or micro or nano gels, beads, capsules, films, sponges, patches. In so many applications, this material can be used. And very recently, I made a trial to print. Here in these videos, you can able to see the printing of chitosan on the substrate of our setup. So this is the first trial that I made. So up to here, the first layer stops printing. It's get completed. So now the second layer started to print. The pressure which I applied to print the chitosan gel is about 1.2 bar, and the printing speed about 80 millimeters per minute, and the layer thickness is about 0.2 millimeters. So after printing, this is the first trial that I made with the chitosan material. So I printed it on the flat surface. So with this result, I started to print the same chitosan material in the petro dish, because we know that chitosan gel is a very soft material. The fact over here is after completion of printing, it's not possible to detach the printed layer from the petro dish unless if we cross-link it. If you try to detach it from the petro dish before class linking, it gets damaged. So to overcome this problem, after completion of printing, I used sodium hydroxide solution to cross-link the printed chitosan material. So here you can find a transparent patch of the chitosan, which is used in healing of different wound problems. Okay. So this is the work we did till now at our institute. So dear participants, if you have any doubts, you can raise. Guys, if you have any doubts, you can raise.
I have one doubt, like
Yesterday also asked same doubt. I think like silk, like it will absorb water. No, sir, it's a hydrophilic. No, how could you incorporate silk fibron in PCL polymer? And
Okay, I got your point, sir. We haven't mixed silk fibron with the water. So silk fibron is a different material, and the material which is used to print the bone scaffold it's a different material. So you just imagine, sir, if you need any product with 10 layers of thickness, so after completion of printing the first layer, we covered the first layer with the silk layer, I mean silk fiber. So after that, we printed the second layer, and the second layer was covered with the silk fiber, and then we printed the third layer. So likewise, after completion of each and every layer, the previous layer was covered with the respective silk, I mean silk fiber materials to for improving for improving the biocompatibilities and biological properties.
the machine itself will fill that one layer
No, sir.
of silk
It's a
fibron.
manual. It's a manual process.
Then, for every layer, you have that fill that silk fibron material, sir.
Yes, sir. Yes, sir. Manually, we had to interrupt the printing process. I mean, before starting the next layer, we have to
Top.
attach on the top of the previous layer. We have to attach the silk fibron. After that, we have to resume printing of next layers.
Okay, 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 okay. Sir, what are all different kinds of works we can do that on that machine, sir? Like,
So whatever the setup that I developed at our institute, sir, you can use this setup to print. So I can tell you the list of materials which can be used in this setup, but I cannot tell you the application and some other details. It's purely connected to your objectives. Sir. So my setup can be used to extrude paste type of material, uh, powder form of polymer, granules form of polymer, sheet form of polymer, or polymer composites, hydrogels.
okay,
So I would like to repeat it once again. So any polymer or polymer composite in the form of powder, granules, sheet. Second thing is paste type. Third thing is, third variety of material is hydrogels.
okay, okay. Sir, can we get? Do we get that required strength, sir, for implants like yeah, said that chitosan or these fibers?
So here, sir, implants were majorly classified into two categories as per my perspective: load-bearing implant and non-load-bearing implant.
Okay,
So
okay,
whatever the products that I developed, all these things were used in non-load-bearing applications, not for load-bearing applications.
okay. So,
So for load-bearing applications, you should use metal implants.
okay, okay, okay. Means we can make unload bearing implant.
No, sir. Will you repeat it? Repeat it again.
Means we can make use of this machine for non-load bearing
Yes.
implants.
Yes, exactly. You can use her, but
Any
how
powders we can blend, sir, in that.
that's what, sir. The polymer or polymer composite powders only, not the metal powders or ceramic powders.
Okay, okay.
If
Polymer
you
powders.
wanted to, if you wanted to develop a ceramic product by using my setup, you have to mix ceramic powder with a binder material. You have to print the product. It is called as a green product. You have, after sintering it at very high temperatures, you will get the required one. At the time of sintering, the bindering material gets evaporated, so you will get
So,
the final product with ceramic material.
same thing, sir. I actually have that objective like blending of the ceramic powder like hydroxyapatite or TCP with polymer. Like
Yes,
we
sir.
can,
So
we
coming to
can.
the printing of the composite that you would like to user. The printability of the material is purely connected with the particle size of the respective ceramic material and the type of binding
Polymer.
material you would like to use.
What kind of
In
binding
the-
material? Like,
So till now, I tried with no, I haven't tried with. I tried with polymer and ceramic powders. I haven't tried with polymer and binding materials to get the ceramic product or green product. I mean green body.
okay, okay, okay.
So
Same
I
thing,
haven't.
sir. I would like to try the same thing, like polymer and ceramic only.
Okay. Till now, that's what I would like to tell you. Till now, I tried with polycaprolactone where it melts around 120 or 130 degrees centigrade. Sir. When it comes to
Okay,
other polymers, sir, like PLA, ABS, and some other, so the minimum melting temperature of those polymers varies from 180 degrees centigrade to 230 or 240. I haven't tried those materials till now, sir, because I
okay,
developed this mechanism to melt uh, low melting point polymers, not for the high melting point polymers. So very soon,
okay,
I would like to upgrade my machine or setup to melt high melting point polymers as well.
okay. So, I'll be in touch with you, sir. Like, if
I'm
you
very
upgrade,
happy
I
with that.
work on that any objective I can frame. Thank you very much.
Yes. Yashwant Kumar Reddy sir, you can unmute your mic and then you can post your
Hello,
question. Yes sir, hi sir.
sir. Is it audible, sir?
Yes sir, audible, sir.
Sir, actually, I am working on polysaccharide, sir. That is natural tree-based gums I am using, sir. Sir,
Okay,
uh, while I am going through the characterization, I found that the melting point of that material is 120, sir. So,
okay.
can we use that in the printer which you have used?
Yes sir, yes sir.
We have that
So
facility, sir, in your organization.
yes, sir, you can utilize it. But the thing is, sir, as I mentioned you a minute back, my system is in a position to heat. I mean, it can go up to 130, sorry, maximum of 140 degrees centigrades only, not beyond
Okay,
that.
sir.
You just send me a sample of your material and I will
Okay.
make a trial of it. If everything goes in a smoother way, then you can take the advantage of my setup, sir.
Sir, one more thing. Other than this melting point, what desired properties should that material have, sir, in order to go for printing? Other than melting point,
So here
that
I would
means,
like to tell you one example, sir.
sir.
In the market, there are two types of polycaprolactones.
Okay, sir.
The first polycaprolactone molecular weight is 80,000, and second uh, polycaprolactone molecular weight is 40,000.
Okay,
I
sir.
tried with both varieties of materials, 40,000 molecular weight PCL and 80,000 molecular weight PCL. When I try to prepare the sample, I mean print the sample with 40,000 molecular weight, I can able
Okay,
to
sir.
print the first layer. I can able
Okay, sir.
to print the upcoming layers because it started to block the nozzle.
Okay.
So I too also don't know the technical reason. And
Okay.
later on, after a few days, I purchased 80,000 molecular weight PCL. When I started to use it, I can able to print multiple layers. Nearly, you can surprise, I have printed a sample with 1 inch of height, nearly
Okay.
25 millimeters of height with 12 millimeters of diameter.
Okay, sir.
So molecular weight of the polymer also plays a major role in printing it.
Okay, sir.
So whatever the polymer you are sending it to me, even though if it melts at 120 or 100 or 140 degrees centigrade,
Okay,
so
sir.
until unless we may not sure that this polymer or material is suitable
Okay.
for 3D printing applications.
Okay. Okay, sir. Thank you, sir.
With multiple trials only, it's possible to
Okay.
justify about the materials.
Thank you, sir.
You're welcome, sir. So, any other doubts? Any doubts, my dear participants? As per this, you will get recorded videos of all the sessions. After completion of entire program, we would like to upload the recorded videos either in Google Drive or OneDrive. So once after uploading all these videos, we will share it to you through our WhatsApp groups. Okay, my dear participants, if you don't have any doubts, we will take a break up to 5 o'clock. And please remember that from 5 to 6:30 we have a session. After completion of the session, you are supposed to give feedback and you are supposed to complete a test from 6:30 p.m. to 7:30 p.m. After that, from 7:30 p.m. to 8 p.m. we have a valid session. It is mandatory to attend the test, and it is mandatory to provide your valuable feedback through your ATAL portal only. Today, we are not at all sharing any feedback links about these three sessions. And whatever the work that you are supposed to do in between 6:30 to 7:30 p.m., it should be happen by using your ATAL portal. I mean, by using your credential through ATAL portal. Thank you, and we will meet exactly at 5 p.m. And please don't leave this meeting. Please stay back in the meeting. Hi, sir. Rakesh, sir. Good evening. Am I audible to you, sir? Hello, Rakesh, sir. Good evening. Am I audible to you, sir?
Yes.
Okay, thank you very much, sir. And good evening, my dear participants. So let me introduce about Rakesh, sir, our today's speaker. So Rakesh K. He has completed his educational qualifications in Bachelor of Degree in Mechanical Engineering, Masters of Engineering in Advanced Manufacturing Systems, MBA in International Businesses, presently pursuing a doctorate in Additive Manufacturing from KL University in the area of 3D printed implants. So coming to his professional profile, presently associated with the National Center for Additive Manufacturing, it is also called as NCAM, as a technical cum industries officer. Previously associated with the Engineering Staff College of India as a senior faculty and head in charge for DPC and mechanical. Previously worked in Design Tech Systems Hyderabad. And prior to that, he was working from Think 3D's head office in Hyderabad. Has dealt with various customers from various backgrounds across India related to educational institute, medical fields, or architectures, etc. In Think 3D, he had played a very vital role in expanding the company in various locations across the India. Mr. Rakesh has immense experience in experimenting with various advanced technologies like 3D printing, IoT technologies, and sharing best knowledge best of knowledge to the client and providing solutions in IoT, 3D printing, advised engineering support to customer to their customers in automobile manufacturing, medical, and architectural fields. Mr. Rakesh has delivered more than 100 seminars on advanced and emerging technologies like IoT, 3D printing, and 3D scanning technologies, and also an industrial resource person for many colleges across our country. Mr. Rakesh is presently having one granted utility patent, three utility patents, five design patents, and four patents in process in IoT devices, one ACA research paper published, and two progressed in medical related fields. So with this brief introduction, I would like to hand over this session to Rakesh sir. Rakesh sir, please.
Thank you, Venkatesh. Is my screen visible?
Earlier it was visible, sir. No. Yes, now it's visible, sir.
Full screen mode?
Yes, sir, you can select it. Slide screen mode, yes. So can you change it into the next slide, sir? Because sometimes it doesn't work. Perfect, sir. Perfect, sir. Thank you.
Okay. Good evening, all. I'm actually thankful to Venkatesh for giving this session and also for coordinating for this program. So today my focus will be mainly on the topic called tissue engineering and 3D printing perspective. And I don't know, Venkatesh, how many are from the tissue engineering perspective or biomedical or biotechnology?
4, sir. I mean, you are asking about number of participants from biomedical technology.
Yes.
Right? Around 5 to 6, sir.
Remaining?
Remaining all are engineers. They are from engineering background, sir.
My main perspective for taking this session is related to the 3D printing only. And I'm not the professional in tissue engineering. I'm the professional in the 3D printing technology. So many corrections related to the tissue wordings or the technology terminology or something, you may correct me. So just want to give you in advance because I'm a 3D printing guy rather than a tissue engineering guy. But 3D printing is the technique which they use for the development of tissue engineering. So it is having a lot of impact right now these days. So I could able to do this presentation with my previous experience, and also I have taken consideration with some of the papers being published globally. I have captured the data which very much relevant and which feels the appropriate to the industry. So I could able to do it so in the complete slide. So just to introduce, thanks for introduction from Venkatesh, and I should also give a slides about my company, which is a National Center for Additive Manufacturing, which is based out of Hyderabad. We are the Government of India enterprise public sector unit, which works under Ministry of Electronics and Information Technology. And this is the epicenter for complete additive manufacturing in India. So we are centrally located and we are the main or nodal agency for development of additive manufacturing in India. Under this perspective, I'll be giving you this session. So this can be moved ahead with the introduction about the National Center for Additive Manufacturing. So as I told you, as we are the government sector, we are very much clear about what government is looking at and why government is looking at this industry and all. So if you see the perspective of additive manufacturing in India, to the right side of the screen, India is just 3.5 3 to 5 points, sorry, 3 to 5% of the global AM industry, which is being, very less when compared to the global economy. If you see the other countries like US, Asia, and European Unions, India is very less in Asia. Also, it is 3 to 5%, which is paved the way to development of additive manufacturing in India. So the main goal, which is being AM market value, is being evaluated from 2021 to 2026, is almost 35.6 billion, which is a very large values. So India standing at 3 to 5% will definitely going back, means going down in coming days. So government of India has focused, and government of India has identified that additive manufacturing to be developed in India. So in this perspective, we are working out, and then we are identifying various companies across India. Almost 300 plus companies are right now developed in Indian entity. If you see the right side of the screen, we have the domestic brands are being developed in India. Slowly, each and every domestic brand is being grown in the perspective of hardware, material, software, and services. If we see the screen, services industry of additive manufacturing, that is 3D printing, is rapid, and people have a number of machineries to produce the parts and then deliver it for you in the various entities. So in this perspective, the service industry is growing, but if you see the vacuum happening at the service software level, you see the people are not able to get this software, which is very costly nowadays. If you take Materialize, Autodesk, or Entopology, or other softwares which are being developed, there are very less companies which are developing the software, which is giving a big impact for us. So NCAM is now working for development of the softwares and development of various other entities. And also, if you see the hardware vertical in the upside of the right side, upper side of the right, you see the companies are being growing there. Even the small FDM based machines, some companies are growing slowly to develop this additive in India. So AM has a additive manufacturing epicenter, National Center for Additive Manufacturing, is working for growth of the Indian AM landscape. So our government of India has slowly given as a big task for getting this 2026 as a target, and they have given us almost 100 plus new startups, 50 Indian specific technologies, 1 lakh skilled manpower, 10 existing and new manufacturing sector to be adopted, and awareness of the adoption of the AM products. So in these lines, government of India has identified us for development of additive manufacturing in India by keeping these startups like 500 plus products. Means one product, once it is being identified, if it is additively manufactured, that is one of the goal being achieved. And then startups, so some of the startups are registered under NCAM. Yearly we are funding them from 10 lakhs to 25 lakhs, and then those fundings are being developed, and then those fundings are all startups are getting those funds, and then they are getting incubated for various AM needs in India. Apart from this, we do have this specific technologies. India need to develop this specific technologies, 50 Indian specific technologies, which are very much required, because we are dependent on the other countries like Europeans or Americans for specific technology. So Indian technology in specific to be developed is one of the main strategic goal which government has given us, and then we are right now started working last year to develop this particular thing. And 1 lakh skilled manpower is one of the new this is the new skilled manpower is required for development of these all initiatives, because skilled manpower is the main human resource which is needed for development of 3D printing in India. So in this skilled manpower, we have started working with various colleges. We have started working with various entities across India for development of manpower. Especially if you see, we conduct the FDP programs, the programs called as ATAP. We funded 2.5 lakhs for each program. We identify certain colleges which they need, which tied 2 or tied 3 colleges. We fund them for the programs of workshops or FDPs, which will be conducted at their locations and will be funded by NCAM. So that is one of the major achievement which we have started last year. To last year, we have funded 25 engineering colleges across India, and we have funded them for development of AM, and FDPs have been conducted. And then next is 10 existing and new manufacturing sectors. This is one of the major initiative government of India has taken, and we are adding these sectors to develop this. Once you adopt this additive manufacturing, you get the benefits out of it and you get the outcomes from it, and then that will lead to the huge business, and Indian economy will grow and additive manufacturing in India will grow. So in this perspective, this goal will lead to the huge impact. So we have started the identifying the sectors, we have started the sectors to adopt, and these things are already in place, and then we are moving ahead for the next things. And next is awareness of the awareness for the adoption of AM products. If you see the awareness for the adoption of AM products, people know about additive, but they are not adopting. So there is one area where we should make them to adopt this technology, which is a hurdle of qualification frameworks, and then we need certain guideline documents. So that is one of the major initiatives which we are taking care to get this certification done, and then this qualification being done, and the framework for adoption of the AM products is one of the strategic goal which we are taking care. So these are the strategic goals which we government of India has given to NCAM. For getting that goals, reaching that goals to the in time, so we have developed 5 pillars. In these 5 pillars, we have identified and kept certain objectives for achieving those particular things. So if you see this, first and foremost, skill development is one of the pillar which we have in NPD, and indigenization is one more product. Enabling adoption and industrialization is one more, and access to AM infrastructure, R&D and innovation is. These are the 5 pillars which we have identified and adopted. And if you see skill development, we have, as I told you, we have been conducting our TEP programs, and the new products are being developed in our facility. The machine is ready, and then we are printing various entities needs, and then enabling adoption and industry readiness, access to the AM infrastructure. We have almost all 24 worth of equipment of additive manufacturing, advanced industry machines, which are being catered for various needs with the open access softwares, which we work on the metal, especially for development of the materials, and then various materials will be developed, and then test coupons will be printed. Those will be tested in the laboratories. And R&D and innovation is one more pillar where we get the startups and R&D for some projects which we are taking up, and then we are funding it. And NCAM is a state government company which is being incorporated as the joint venture between Ministry of Electronics and Information Technology and Government of Telangana in partnership with the industry. Major vision for this NCAM is to develop comprehensive additive manufacturing ecosystem in country and position India as a global AM manufacturing hub. So this center is inaugurated 2023, 8 June 2023, and we have raised a certain amount of investments also, and we have almost conducted 40 plus workshops, seminars, conferences, and also impacting almost all 12,000. It's now almost all 20,000 right now. We are getting the companies to India, and first cohort and second cohort is right now working for development of the product. We get the idea being incubated at our place, and then product viability, and mentoring the business planning, and then IPR generation and mentoring and technology commercialization. So these lines we are very much working out, and then we do work for the Invest India, where we get the other countries companies doing registered in India. So we conduct various conferences across India for industry and academia and medical, various people cohort. And then we do workshops, especially with the software workshops. If you see materialized works, if you see related to the biotechnology, it's definite and mandate for the people to work on the high quality softwares, materialized softwares, which they have to get the outputs for working for their biomedical people needs to have the idea about the materialized or universal or mimics or magic softwares, which will impact their growth and development of the scaffolds or various things. Anyhow, I'll be discussing in the coming points. Apart from this, we do have the conferences which we work up across with collaboration with the industry, academia, and also the companies which we work for, the Orthodontics and Prosthetics of India, and various companies which we are working at. And we conduct the international conferences with NIT Warangal, AITS, various companies, various academias, and then this is one of the conference conducted in 2024 in NIT Warangal. So just getting into our subject, what we have discussed and what we are working at. So tissue engineering process, maybe this will be morely into the engineering perspective or a biomedical or biotechnology perspective. If you consider these tissue engineering process majorly revolves around this sequence of activities or process which is being involved for the biomaterials, fabrication methods, scaffolds, and then in vitro culture and functional tissues. So this is the main process flow, what is being considered in the tissue engineering perspective, where various people work on it, and various people know on this process. But still, technical perspective, if you talk this tissue engineering in most probably we see the tissue engineering being collaborated between the mechanical fabrication and then the materials combination. These two combination, if you see the regular fabrication methods, you see 3D printing, electrospinning, phase separation, freeze drying, self-assembly, solvent casting, material injections, and these are already involved in one of in the fabrication methods. But now these techniques which we are discussing, or these techniques, these engineering processes, whatever we are seeing, these are being adopted with advanced technologies like additive manufacturing. Because if you see the perspective of 3D printing, this is scaffolding of the tissue engineering. There are so many transplantations, organ transplantations are being waiting. So there is a slight advantage if you see the 3D, if you attach this 3D printing technology to this organ transplantation, there are certain chances in future that there will be definitely a global increase, and then this 3D printing will definitely have the advantage. Because you see long wait of this organ transplantation like kidneys or liver or something, people are working at. We are not sure how much it will be having, but definitely the scaffolding or the designs of scaffold or the processes which are being involved for development of this various scaffold techniques which are being incorporated with additive manufacturing techniques. We are developing the constructs like skin, we have a ear, we do have cartilage, bones, cartilage. So various scaffolds are being developed using this additive manufacturing, 3D printing, bioprinting technology. And we see ocular, like 3D printed retina, and some of the highest high-end institutions like IITs and IITs are working on the bioprinting technology, which is being taken care for development of new things. So if you see the schematic illustration with, I guess, biotechnology people may be knowing on this, what exactly happens, and people in engineering may be having an idea on this, which what happens between the complete the scale drugs and then biomolecular formation, what happens between the cells, polymers, and biomolecules, and then engineered polymer construct. If this happens, then definitely there will be a complete drugs, biomolecules, and cells released into the vivo. This is the sequence. Normally, this schematic illustration, what the cells and then biomolecules formation happens in the regular 3D printing perspective. Not only 3D printing perspective or your regular manufacturing the tissue engineering. So this, whatever I have showing in this, there are so many for achieving this particular vivo or the final delivery or the product from with this particular cells and polymers combined with the biomolecules. There are certain processes and then fabrications techniques are being used in the market, like various techniques. If you see, there are bioprinting, forming, self-assembly, extrusion, phase separation, electrospinning. So these are the regular scaffolding mechanic techniques, what we call it as. And if you see popularly these days, electrospinning is very popular, where the complete syringe will be having the material, and then polymer solution will be holding, and then nozzle will be printing on it, and then the complete the polymer fiber will be layering on the plate, and then that will be a non-woven type, and then that material will be syringe will be using. So the major electrospinning technique is one of the famous techniques which is being used for various materials like polychlorolactane, PCL, what we call it as, and also PVDF, that is polyvinylidene fluoride. Sorry if I am spelling it wrong, maybe. I could not twist my tongue. Apart from this, we do have polymethyl methacrylate acrylate, which is PMMA, what we call it as. These materials which are being used in various forms, and no, they are being used in different techniques also. We do have various techniques in 3D printing, but these existing techniques, which they have already started. If you see the scaffold formation techniques, what are the main advantages and disadvantages which we are having? Left side, if you see the electrospinning technique, which is being used for majorly bone, nerves, skin, cartilage, tissue engineering. And there is a very high advantages in electrospinning technique, majorly because of the high surface area to the volume ratio, high porosity, easy process, which makes the complete process easy by getting the scaffold formation. And this electrospinning technique is used this is not a new technique, but this electrospinning technique major advantage is high surface area to the volume. And apart from that, we do have very bad disadvantages. We have only few polymers which can be used in the electrospinning technique, where there is a viscosity being played, and there is a lot of viscosity issues which you consider while the polymer is coming out from the nozzle solution and polymer being mixed and then coming out from the needle. So apart from this, we do have a method called phase separation, which is a protein delivery application or a drug release, which is a bioactive agents can be incorporated into structure with a high porosity, and then limited range of porous size problems with the residual solvents. This is a big disadvantage which we have, because there is the pore size is very important, and then residual solvents which are being formed inside the scaffolding will be a challenging this. So this is the big disadvantage which we have in the phase separation technique, where the bioagents are incorporated into the structure with high porosity. And coming to solvent casting, this is used for the vascular tissue engineering applications, which we see regularly. These are the introduction which I am speaking about. It continues with the 3D printing. So this is a very simple method and control porosity. But when you get the material out, the mechanical strength and thickness and limited thickness, if you go with this, is and small pore size. These three are the issues which we see in the solvent casting. Even in some of the printing applications in 3D printing, we see this method being incorporated with some other addition of the 3D printing technique, where you get the solvent casting being method being incorporated and added with the 3D printing XYZ systems, making 3D to get the more strength. And then there are so many researchers going on. So this is the scaffolding formation techniques which are available in the market and which are being used. So just that is it. I had given the introduction. If you come to the exact what the 3D printing of tissue engineering scaffolds is all about, there are so many 3D printing techniques which we have, like FDM, SLA, SLS, DMLS, DMP, they call it as, powder bed fusion technologies, digital lead processing technology, stereolithography, selective laser sinting technology. So there are multiple technologies which we are having right now. These multiple technologies, all technologies may not be used. If you have considered any point of view on the perspective of the 3D printing for tissues, especially for the scaffolding, there are few things which can be easily used, that is bioprinting and techniques applicable for it. If you see to the right side of the screen, there are bio ink and then inkjet. So ink based bioprinting is one technique which is popular for bio applications, and people are working on it, and they are already some of the high institutes are working on it. And there is one more application is uh, laser assisted bio ink. If you see, the upper layer is laser pulse, and then donor layer, and then bio ink, and then it forms in the laser assisted, where it has to be layered. And this is the very popular technique in the tissue engineering, people who are working with the tissues engineering scaffolds. And there are certain material constraints in this laser assisted bio printing, where due to the laser, the properties of the material or the bio ink is being distorted or they are having some issues. And there is one more material is extrusion-based biomaterial. If you see the laser-assisted extrusion, if you see, sorry, extrusion bioprinting, if you see, this is one of the techniques which is common where you have a syringe and then syringe material is mechanical force is applied and then syringe will be moving as per the design, whatever you have incorporated. One second. So in this, what happens is this this extrusion based material is popular for tissue engineering because the properties being achieved because of the mechanical force on the syringe and then bio ink being layered on the extrusion area, which makes this process very simple and then we get the output of it because the nozzle dia or the nozzle material being extruded from the nozzle is very critical in this extrusion system. And then how much you can control your mechanical force and then how much fast your layering happens on the build plate is the major one where the tissue engineering scaffolds are being 3D printed. We go to the next is stereolithography, what we call as SLA in the popular phenomena, which is being used for the bio ink mechanism where bio ink will be in the tray and then laser will be hitting on the build plate and then we do which is a complete light source and then light will be hitting on the build plate and the objects are being formed or the scaffolds are being formed. So this stereolithography major your advantage is the media. Media are the resins or materials which are biomaterial resins, which are being helping for the development of the scaffolds with that particular tray. And if you consider on the next technique is nano, which is advanced, I did not mention here. Nano 3D printing, what they call as, or micro 3D printing, what they call it as. The companies from the Israel are concentrating more on development of this nano printed bio printing techniques, which are now bioprinting techniques, SLA, and these things are bit back on when you go to the nano printing where your scaffolds are very, very small and then the dia of the thickness of the scaffolds is very less. So micro 3D printing or nano 3D printing is one of the advanced technologies right now which they are working at. So coming back to the first one, that is inkjet, second one, sorry, inkjet bioprinting. This is the popular one again, apart from the extrusion technique which people are using in the tissue engineering. Why I'm coming back to this inkjet is inkjet, if you see the piezoelectric activator is being used and then bio ink is being moved out of and then the droplets are layering on the layer by layer, it forms the object. So this tissue engineering scaffolds popularly in 3D printing right now, whatever I have shown, this inkjet and then extrusion, these two 3D printers techniques or 3D printing techniques are being popularly deployed for development of scaffolds in bioprinting technology. And if you go to the other techniques, if I talk about, this is FDM, people are working on. FDM is a regular thing. What they are doing is they are printing the external surface of the structures of the scaffolds and then they are developing certain other structures in between. That FDM is one of the popular technique which is being used for the microfiber extrusion methods, and the other one is microfiber extrusion methods which are also being used for development of the very fine fiber materials. And then if you go to SLS technology, SLS technology is also used for development of scaffolds, especially if you go to the prosthetics or any other thing where you need to have the scaffolds for prosthetics. Scaffolding designs and everything are being designed, and then you are getting the object 3D printed in the SLS technology. And melt electrospinning technique is one popular technique which is being adopted with 3D printing additional, which they are right now being taking the advantage because this whatever we are doing this previously in electro spinning technique, it is popularly called as, now it is popularly called as 3D tissue engineering scaffold fabrication technique, being alternative for the previous solution electro spinning technique, which is called as SES. And then previously, if you see on the major disadvantage related to the toxic polymer solutions, that is residuals, chloroforms, PCLs, and then DMSO, that is dimethyl sulfonoxide, and then dimethyl fluoroamide. These materials are, these are the toxic solutions which are being, disadvantages which are having for the development. So with the melt electrospinning, which is relatively now called as 3D TE technique, what we presently people are using. So they have almost all recent works, they have literally found the solution to get a diameter less than 1 micrometer. It is the one of the classic solution being given from the electrospinning perspective, which was the previous general development perspective, where they have received almost, depositing the layers of with less than 1 micrometer. This micrometer, whatever I am talking previously, when you go with the solution-based stirring or the solution-based solution electrospinning, what we call it as SES, and right now this melt electrospinning MES and then SES, there is more advancement in 3D printing technology, where your SES cannot achieve that. What we talk, the main focus is the thickness and then the issues in the tissue development. So that has been, taken as advantage, where people have started are getting this advantage of this melt based scaffolding method. To just summarize with the this is taken from one of the paper, guys. I just want to inform you. This was discussion, as a discussion I'm telling. This was one of the paper which I was there for their needs, so I just adopted this into this one, in this session. If you see the summary of the technique and then application advantages and disadvantages, just as a tabulation column, you see the method is bioprinting. You have this scaffold manufacturing, hydrogels, tissue engineering, and cell growth, which can be the major application in bioprinting, and prints viable cells of the soft applications, which is the biggest advantage which we have in this bioprinting. And coming to disadvantages, if I talk about required support structures, nozzle limitations, must be a psychotoxics during process. But nozzle limitation is right now almost all achieved. I guess recent days people are able to cross that nozzle limitation issues, where they are able to take it up into the next level of it, and then they are manufacturing the process, scaffold manufacturing a hydrogel, and the tissue engineering is being moved into the next level. And next, if you do the extrusion-based methods, right now the applications majorly are holding on pharmaceuticals, again the scaffolding, and then bone tissue engineering and cardiovascular medical devices. These are these three processes are being followed for process according to the complete applications. And a major advantage which we have in this one is the major advantage versus the bioprinting is cytotoxicity, toxicity. And also it's very low cost extrusion based, as I told you, and it's a very inexpensive printers are being used for developing. But the extrusion based has very inaccurate resolution, I can say. Accuracy is very challenging. And next one is the only thermoplastics can be used, and non-biodegradable materials can be used, and then post-processing is a very big challenge. So post-processing, your main structures are being distorted, and then extrusion issues are being seen on this particular thing. And next is SLS techniques, or selective laser sintering, SLS, SLA, what we call. These are also people talk in bioprinting as indirect methods, but coming to 3D printing technology, SLS and SLA are the major market growing industries which are there in the market right now. Next is indirect techniques. These are being used for pharmaceutical, again, biomedical manufacturing, bone tissue engineering, pharmaceutical drug delivery. These are the major applications which people are doing. And the major advantage what we have is high mechanical properties, SLS powder supporting the structure, and then high resolution and smooth surface processing, shorter time for processes. But the worst things which we observe in SLS is photosensitive materials, in SLA, photosensitive materials, and they are very expensive. Machines are being SLA machine starts from 10 lakhs and reaches almost all more than 60-70 lakhs, which is very challenging. And then And if you have very complicated structures in the printing areas, there may be certain challenges where your edges are challenged, because in 3D printing, when laser is moving, or your very complicated structures, I'm not telling 3D printing will not do the complicated structures. Coming to the size of the microns, if you take about a nanomicron size, or one micrometer size, we take, there is a challenge where your object cannot be achieving your exact design of which we are supporting at. If you see the support systems which are being very complicated